Okay, well, thank you. Thanks for inviting me to the workshop. So this talk is based on the work of two of my students. Shripad is actually right here in the audience. And Lily graduated recently, but the latter half of the talk is based on her work, if I can get to it. So the focus of the talk is on distributed optimization of cost functions that look like this. And you have seen functions like this already several times. By the way, I don't have very many equations in my talk at all today, and it's motivated by a discussion I had with somebody about teaching calculus without equations, and I thought I can do talks on optimization without equations too, maybe. So we'll see if it works. Okay, so I don't think this audience needs this kind of background, but I have my slides. So there are many applications of these kinds of cost functions. The one that hasn't come up yet in this meeting is robotics. So if a rendezvous problem where a bunch of robots need to meet somewhere, maybe it's people who want to meet somewhere, and you want to minimize the total cost of meeting at a particular location X, then the cost function Fi, if I am agent I, that's my cost function of getting there, and you want to minimize the global cost function. And machine learning application has been brought up today, but there are many such applications. In this case, perhaps each of us has some data. This is pictures from, I think, CFAR. And you want to optimize some cost function or loss function over the data that all of us have. But I don't want to share the data with you, perhaps. And the question is, how do you do it? So this is the outline for the talk. That's the problem we are dealing with. I'll introduce what I mean by distributed optimization with some pictures. And that should be familiar to all of you. Then I'll talk about privacy. That actually continues the theme from before. And then I'll get to fault tolerance if there is still time. And with fault tolerance, what it means is that if one of the users is compromised, provides bogus data, then what does it mean to do distributed optimization? What do you really achieve? So there are a couple of different architectures that we have seen already yesterday and today. One is a server-based architecture. You have a bunch of clients that have the data. The server is just helping them to perform that optimization over the cost functions that all the users know. And here you have a peer-to-peer architecture where there is no central server, but the client somehow, the user somehow collaborate to get to the optimal. So I'll start with the client-server architecture. So here is an algorithm that all of you know, and there are many variations on this, but just to introduce my pictures, my notation. So we have a server, a bunch of clients, and there are 3 clients in this picture. Each of them has a local cost functions that I'm calling F1, F2, F3, or Fi in general. And this cost function may be derived from the data that the user has, but we don't care about the data right now. And here is the sort of the trivial algorithm that works in each round. First of all, the server keeps track of its own sort of the estimate of the optima. So initially, it could be whatever you want. And in each round, if you're a client, you download the current estimate. You compute the gradient of your cost function at that estimate and upload the gradient. And then the server aggregates all those gradients and does the descent step, right? So this is all very familiar. Of course, there are many variations that have been discussed already, stochastic, asynchronous, and what have you. In the peer-to-peer architecture, similar things happen. And instead of having a server, each user maintains his own estimate. They exchange the estimates, perform a consensus step using this doubly stochastic metrics. I'm assuming undirected graphs here. And then what is different is that each client will apply his own gradient to that averaged estimate. So now let's get to the notion of privacy that we are dealing with. The way I presented the client-server algorithm, and this problem applies in slightly related ways to the peer-to-peer system as well. The issue here is that the client is uploading the gradients to the server. And if you send me enough gradients of your cost function, eventually I can figure out your cost function, right? So I can use the gradients to, if the gradients come from a polynomial, let's say of degree 1, then I just need a couple of different gradients sort of to figure out which line is your cost function, right? So you can see how knowing gradients might divulge information about your cost function. The more gradients you send me, the more I can learn. So sharing information with the server sort of compromises privacy, and we do want to protect privacy and yet optimize whatever cost function we set out to optimize collaboratively. So there is a lot of related work. We are not the first to think of it, and you heard the talk right before mine. There are cryptographic methods using homomorphic encryption, which basically means that you perform computations on encrypted data, and yet the outcome of the, if you decrypt the encrypted computation, you get the right result. There is so-called function transformation where I have a cost function, I change the cost function to something else while keeping the minima the same. And then I give you that new cost function, you solve that function for me. You don't know my function, but I get the right answer back. And differential privacy, we heard about that today already. But here is one version of differential privacy, just to compare to what I'm going to present later today. We saw the algorithm just now where the clients upload gradients. And now instead of uploading the gradients as they are, you add noise to those gradients. And the server will do what it does. Now in this particular method, to get to privacy, you make, first of all, this noise is usually, well, at least all the methods I know, the noise is added with zero mean, Laplacian typically, Gaussian maybe. But if you want to achieve privacy, then you need to give up something on accuracy. And by accuracy, I don't mean accuracy of classification. You can get to accuracy of classification in many different ways. Here, by accuracy, I mean that I'm solving the exact same optimization problem I set out to solve. Right? So you can solve something different, and if you're doing machine learning, you could still get very good accuracy of classification. But here, by accuracy, I mean that I had a particular cost function that was summation of fi. I want to solve that exact cost function, not something close to that. And to get there, if you want to achieve privacy with this method, you have to trade off on accuracy. So actually, we did work on differential privacy. I think there was a paper in 2014 which gives you this trade-off. But the paper, the way we presented it, was in a peer-to-peer setting, not client-server. But you can apply similar ideas to client-server. So the approach that Shripad is exploring is a sort of on a different axis. We are providing a different trade-off now. And the approach is motivated by something called secret sharing in the security domain. The basic idea behind this work, Shripad's work, is to exploit diversity. And by diversity, we mean in the case of client-server model, we're going to assume there are multiple servers, not just one. And I'm going to exploit availability of multiple servers to provide privacy. And in case of peer-to-peer networks, the network is rich. I have many neighbors that I can talk to. And I'm going to exploit the possibility of having many neighbors to provide privacy under different assumptions than we have seen before. So for the client-server model, we assume multiple servers. And there are a bunch of clients trying to optimize something. So here you have to imagine these two servers belonging to two different entities, right? Two different providers who don't cooperate with each other. And we, as a group of clients, want to solve a problem. But I don't want to trust either of those guys. Right? So I don't want to give the data to somebody, to the cloud, and say, do it for me. I don't want to share the data with anybody at all. So I don't trust either of them. But I expect them to follow certain rules. In particular, I want them to not tell each other everything I'm telling them. So whatever I send to you, I don't want you to forward to him, because you're sort of prevented, hopefully, by etiquettes or rules or laws or something like that. So in a sense, you're going to pretend that or assume that not all the servers are adversarial. Maybe one of them is, maybe two of them are, but not everybody is adversarial. In the case of peer-to-peer, same idea. I'm one of the entities in the network, one of the agents. I'm going to assume that not everybody around me is compromised. If they are, then of course, I'm not going to get much of privacy, because everything I say is divulged to the adversary. There is no way to get privacy, at least in our model. So the approach is actually bears some similarity to the previous talk. The idea is to add structured noise that cancels over all the servers or neighbors that we're going to talk to. So that's the high-level bit. Shripad has many variations on this, and I might allude to that later on. But let me give the intuition behind why this might work with this simpler mechanism. So here is a setting with two servers, three clients. And in this picture, each client is connected to both servers. You can generalize the ideas to more general topologies, meaning there may be 4 servers, and I talk to only 2 of the servers, and you talk to other servers, and so on. So this topology is just for an example. So how would you use this system, forget privacy for the moment, to solve the optimization problem? The algorithm that works actually, didn't I have the, OK. I thought I had one more slide. OK, so the way I'm going to illustrate the idea is that this is what we want to solve, F1 plus F2 plus F3. We're going to have each of these clients pretend to be 2 people and simulate 2 different clients. right? So this guy here, this yellow client, had cost function f1 is going to simulate two clients now with function f11 plus f12 adding up to his original cost function. Each of these simulated clients connects to just one of the available servers. Now, if you look at this picture, this is just a very standard multi-server architecture where one client talks to one server, and of course, the servers are connected to each other through a network as well. So this particular system can easily solve the problem that we set out to solve, even if these component functions, f11, f12, are not convex. This still solves the original goal. And here is the algorithm. Again, it looks very familiar. I have presented this once already. Each server maintains an estimate. Each client downloads the estimate. And when I say each client now, I mean each of these simulated clients. Each client downloads the estimate from his corresponding server and computes the gradient of his cost function, in this case f11, and upload the gradient. The server does the usual thing, receives the gradients, accumulates them, does a gradient step. And then they have one more step now. Because they have multiple servers, they must do consensus. And by that, I mean average consensus. So you exchange the estimates, do a weighted average. And this converges to the optimum of the original cost function under sort of reasonable assumptions. And one of the key assumptions we make is that the gradients are Lipschitz continuous. We need that for this to work out. So this is the sort of the intuition behind what we are trying to do. The difficulty is, well, actually, before I come to the difficulty, what kind of privacy do you get here? So if you notice, this server 1 is talking to f11. So meaning, in principle, it could learn f11 cost function completely, right? If he has enough information, it could completely learn f11. This guy could learn f21, f31 as well. What's happening between these two guys? So what does server 2, or let's say, what does server 1 observe about f11, f12, f22, f32? Server 1 does not talk to f32, meaning the client with cost f32 at all. The only communication server 1 has with this guy is through server 2. But server 2 only presents cumulative information over these three cost functions. So in principle, if you grant me that the server 1 will learn as much as possible, what's possible is that he may learn each of these individual functions, f1, 1, 2, 1, 3, 1, and the sum of these three. But that's not really enough if you're careful to sort of reverse engineer any of the individual cost functions, f1, f2, f3. Does that make sense? Yes.
So can you always ensure that the local cost functions can be written as sum of two cost functions?
The question is, can I always ensure that a local cost function can be written as two cost functions? That's trivially possible because I don't require them to be convex.
Okay.
However, so if you take f1 and write as a sum of two cost functions, does picking any two cost functions suffice to give you the privacy you want? That's a slightly harder argument. So today I'm going to present only the correctness claims, meaning the fact that we get to correct. Now the question is, so first of all, you can write it as sum of any two cost functions. That's trivial, right? So
over all values of x?
no, I mean, this is, I mean, think of, suppose my f of 1 is x squared. I'll just say, give me f11. Whatever you give me as f11, I'll just make f12 to be f1 minus that function. So it's trivial to come up with these functions. The real issue is, does the choice of the broken function, sort of the partial functions matter for privacy? It does. So in to give an example, if
I mean, the other function that you will get may not have the right property. For instance, I mean, you also said, so now these individual ones also have to have Lipschitz continuous gradient and all that?
Well, no, the individual ones, actually, this particular scheme, if you analyze it this way, yes. I'm just motivating this to give you the scheme that we do have. In fact, this is analyzed also under the assumption of Lipschitz continuousness. You're right. Individual cost functions have to have that. But another way to maybe motivate this, imagine that your cost functions are polynomials of degree 10. Right? Then I can pick f11 to be a randomly chosen polynomial of degree 10. And then f12 to be f1 minus f11, which will also be another random-looking polynomial of degree 10. And then all this works out. Right? OK. So this is sort of the way to motivate what we're trying to do. However, doing functions, this is what we call function splitting. It's not always that simple because to even enumerate, like, first of all, this requires that each of these be functions, meaning for every value of x, you must spit out the same value. And to be able to do this constructively, essentially you need to enumerate the function or have a way to describe the function in a compact way. It's not always possible to do this. And so that motivates the so-called structured randomization. So there are a couple of ways to add noise, and I'm going to present one of them. You can do multiplicative noise, you can do additive noise, you can do both together. But the goal is that the noise should just cancel out somehow over space and over time. So here is the example again, same example. So we have two server C clients. I'm just going to focus on one of the clients and tell you what it does in the upload step, meaning, as you remember, in the baseline algorithm, without the splitting, I'm not splitting anything anymore. My cost functions are what they were, F1, F2, F3. If you remember, in each iteration, the client will download the estimate from each server. In this case, it will download from each server, so it gets two estimates. And nominally, it would upload the gradient of its cost function F1. And we're going to change that and add some noise to that step. So I'm just going to focus on just client 1, forget the other connections for the moment. And this is what client 1 does. So the estimates maintained by server 1 and 2, I'm calling them X superscript 1, X superscript 2. So the client will download those two estimates, compute the gradient of his own cost function. And in this case, the noise is multiplicative. And by that, I mean that I'm going to multiply my gradient by some arbitrary constant alpha and beta, such that they're constrained, so they must add up to 1. Now, if you have many servers, I still have the same constraint. So if I have 3 servers, then I'll have alpha, beta, gamma, and multiply each of those gradients with those constants so that they add up to 1. And that's what I mean by canceling out. Okay, so now, even though here, in my example, I require that these multipliers add up to 1 in this single iteration, that's not necessary. As long as they add up to a constant over a fixed number of cycles, fixed number of rounds, that still gives the same result. Okay? And the other key thing which differentiates this from differential privacy is that this noise. So if you think about what this server is, a client is, what's happening on this link from client 1 to server 1. If you made alpha equal to 1, the client would send to the server number 1 noise-free gradients. Multiplying by alpha can be thought of as sending noisy gradients. This noise doesn't have to be zero mean for this particular algorithm to work. And that's what differentiates this from differential privacy. For differential privacy, for things to work out, if you want to get reasonably correct results, you must have zero mean noise. At least the schemes I know, they all introduce zero mean noise. So again, under assumptions that I said earlier, the main assumption is that Lipschitz continuous gradients. This thing works out, you get the right optimal, meaning we are solving exactly this problem, not something close to that. Okay, there is no approximation of optimality. Okay, are there any questions on any of this so far? Yeah.
So what do you mean by solving? So
Solving as in, I mean, these guys, so what's happening, are servers, they have estimates. It's just like any other algorithm that you know, distributed algorithm. In the limit, the estimate at each server reaches an optima in this.
by optimal, you mean the stationary
In this.
solution or global optimals? Because this is a non-convex, right?
Actually, I'm waving my hands too much. So we assume that sigma fi is convex.
Oh, I see.
Okay? Or even fi is convex. You don't need that, but sigma fi is definitely convex. Yeah.
Do you get any kind of guarantee about what you could infer about the client's data? So for example, if f of xi was 0, that's the only case where you can see 0 as your...
Which is why we have additive noise also. Which is why we have additive noise too.
Okay, additive noise.
Yeah, yeah. So that's the reason you need additive also, is exactly for that case, that when the gradient is 0, multiplying by anything still gives you 0. And so it diverges something. But actually, the question is still very interesting because the way I'm stating the problem is that I don't want you to learn my cost function. Now, if my cost function is a degree 10 polynomial, and if you learn the first 9 coefficient and just not the 10th one, I can still claim that you haven't learned my cost function. But you still have learned a lot about my cost function. So
The cost function is a proxy for the client's data? Or?
if you're thinking in your context of machine learning, certainly yes. Yes, it is. So the question really, and I'm sort of punting on it a little bit, is that if you have arbitrary cost functions, what precise statement can you make about the privacy we provide? That we haven't actually, we have claims for, let's say, polynomials. We can make precise claims. For general setting, we think we know what to say. Hasn't been written down. So hopefully in a month, Shripad will have this paper somewhere on archive. Yeah.
Do you have to, in the splitting, do you have to do the splitting at every iteration or once
Well, this is, well, so there are a couple, when you say splitting, let's get specific. Are you talking about this scheme or the one before? Before. Okay, the one before was where I have statically chosen functions, right? And then, of course, they're one-time decision, where the key is that by function, what you mean is that if I give you an x, right, the value you compute will be always the same. This is, in a sense, a simulation of that, with the key difference that if you give me this parameter x1 equal to, let's say, 0, all 0 vector, and if today I use alpha equal to 0.5 for that, tomorrow you give me all 0, I might use 0.7 for that. So in some sense, this is, you can think of this as, if you want to connect the two ideas, it's like I have split that is dynamic and randomized, non-deterministic. Right? So that's the way to map. So in fact, someday we will take these two ideas and sort of write one unifying paper. Basically, that's the way to do it, is to say that you're splitting the functions every iteration with a choice of function, maybe time varying, but with some nice properties. And the nice property here is simply that these coefficients sort of add up to a uniform constant over some amount of time. Okay, any other questions? Yeah.
So for the server, if you have more than 2 servers,
Yeah.
will the privacy get to be better?
Well, it depends on what you mean by better. But basically, there are a couple of ways of doing this. Right? So if I have 10 servers, then in the limit I can give you, I can make it so that as long as one server is not compromised, you get privacy. Then I have to talk to all the servers. Right? Or you can give me 6 servers. I talk to servers 1, 2, and 3. She talks to 4, 5, and 6. And if I'm talking to 3 of them, then as long as not all 3 are compromised, I get privacy. So really, essentially, you get privacy so long as not all the servers you talk to are compromised. So yes, more servers will give you tolerance for more. But of course, you need more servers, right? That's not free. So you need at least, for this thing to work, you need at least 2 servers. One server won't do it. And that's the nice thing about differential privacy, that you get differential privacy even with just one server. Homomorphic encryption will also give you privacy with just one server. This idea will not give you privacy with just one server. So we are paying somewhere. It's just a different dimension. OK, so similar techniques work for peer-to-peer setting as well. We have seen this algorithm before, right? The clients, the users, each maintain their own estimate. They exchange the estimates once in a while. They do averaging, weighted averaging to eventually compute global average. And in every step, every client will apply the gradient of his own cost function. So that's the key difference here. But if you think about it, even this kind of algorithm can divulge information about your cost functions. And the question then is, how do you privatize that? So Shripad has 2 versions of this algorithm that actually he will present a poster today. But let me just quickly just look at the yellow boxes for the moment. This is just the one step of the algorithm that matters. So as you recall, in this algorithm, in each round, if you're a user, you send your current estimate to all your neighbors. And of course, you send it faithfully. The estimate that you have as it is noiseless. What we do in this particular version of the algorithm is that we add noise to each of the neighbors that cancels over the neighbors. Again, so essentially the noise is canceling over space, but you can add time too, meaning it doesn't really cancel all in one shot. It could cancel over time. So that's one version of the algorithm. Now, the nice thing about this version is that I can compute this epsilon 1, epsilon 2 just by myself. I don't have to talk to you to know what noise I should add. As long as the noise I add to all the neighbors add to 0, this works correctly. So there is no extra communication required per se. But if you want to do something different, there's a global version of the algorithm where you talk to your neighbors and then compute the noise you will use. So these 2 algorithms have a different flavor, but you can talk to Shripad this afternoon or evening, I think. When is it, today evening or evening? Yeah. And he'll go over those 2 algorithms in more detail if you like. And I think I have some more time, is it? Yeah, how much time do I have? Oh, more than enough. Actually, this never happens. I always run out of time, so this is good. OK, so the last part of my talk, so-called fault tolerance. And so I should give you some background for myself. I'm not from this community. I come from distributed computing from the computer science perspective. And it's a parallel universe where people also work on consensus. And this community works on consensus too. And we've been trying to do things at the intersection of the two domains. So for example, in my community, we work on fault-tolerant consensus. Byzantine fault-tolerant consensus is a very old problem, 30-year-old problem, right? 1980, I think, was the first paper. But Byzantine fault-tolerant consensus over directed graphs wasn't even looked at until recently. And there are many, and there are versions of this problem that are still open. So let's say vector, if you have vector inputs, and if you want to do Byzantine fault-tolerant consensus, we know how to do it on a complete graph, meaning where everybody can talk to everybody else. But on incomplete, or in particular directed incomplete graphs, the problem is still open, right? I mean, this is after 30 years of work on consensus. So it turns out these two communities have stayed far apart for too long. We were trying to bridge the gap. But that's how I started working on all of this stuff, that someday I realized that consensus is like optimization. And so the question we were asking is, how would you do average consensus if one of the agents provides bogus value? What does it mean to compute an average if I don't provide the correct data? And then that led to this. So the idea is that you're trying to solve that sigma Fi problem, except that some of the entities are compromised, they're faulty, and they might produce bad communication, right? They might send you bad things, and yet you want to produce correct output. And the question then is, what should correct mean? And so we have one notion of correct that I will just define, not get into any details. But this is the so-called Byzantine fault model. All it really says is that if an agent is compromised, it can do anything at all. There are no constraints. There are no power constraint on the adversary. Some people in consensus look at power constraints, meaning that if I'm supposed to send a 0, I get to add only plus minus 2 to that value, and that's the power constraint. In the Byzantine model imposes no such constraint. You can do whatever you like. You can talk to all the other bad guys for free, right, instantly, and coordinate your attack and so on. So for example, if you're solving this problem of meeting for dinner, right, so I could choose my cost function, whatever I like, in the context of optimization. So I'm from Illinois, right, from Champaign. I could pretend that my cost of meeting in Champaign is 0 and is very high everywhere else. So I can drag you all to Champaign for dinner tonight, right, if you're trying to minimize the global cost. Obviously, that's not a good way to meet. And same thing can happen in the client-server architecture too. In fact, I was going to ask this question at the end of the last talk. If we do client-server computation, and if one of the servers provides bad gradients, it's going to essentially produce wrong outcome from this computation. One bad client can be enough to change your outcome quite a bit. Of course, you can get many bad clients when you're working with random people. So you have to somehow filter these bad things, bad gradients. Okay? So the original problem is not really meaningful anymore, right? You set out to optimize the sum of cost function over all agents. If I'm a bad agent, you don't really want to account for my cost. You want to essentially just ignore my cost function completely. So what you want to optimize is this. You want to optimize the sum of the cost functions over only the good guys, okay, the non-faulty agents. Except that the good guys don't come with labels saying he is good and he is bad. Okay? I mean, some bad behavior is so obviously bad that you can filter them. But if I'm a smart adversary, then I'll stay within your constraints. If you say your function has to be Lifshitz continuous, blah, 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 I'll just pick a cost function that satisfies all those requirements, but do the worst possible damage within those constraints. So the good guys and bad guys are not distinguishable just looking at what, you should not assume that they're distinguishable just from what they send you. So you can actually prove that there is no algorithm that will optimize this cost function because you don't really know who the good guys are. So in some sense, if you allow me that of the n people in this room, let's say T is the threshold for how many faulty agents there are, then allow for any T of U to be faulty, right? I cannot assume these T are faulty or that. It could be just any T at all. And yet the algorithm should be correct. So if you know Byzantine fault-tolerant consensus, this should sound familiar because that's how we define fault-tolerant consensus there. But I'm extending that to optimization now. So given that this is not solvable, question is, what can we do then? I'm sure there are, if you start thinking about this problem, you will have your own favorite definition for what does it mean to be fault-tolerant. And I know that in machine learning, people do robust machine learning, and they have their own way of defining robustness as well, which somehow seems to be related to this too. So one way to think about what we are trying to do here, we are trying to optimize a weighted average of the cost functions of the good guys where the weights are equal. The weights are uniform. And I'm claiming that that's not possible to achieve. So I cannot optimize weighted sum of good cost functions where the weights are equal. So you have to allow me unequal weights. Okay, so I'm going to not optimize that function at all because that's impossible. I'm going to optimize a weighted sum of the good guys, right? Where the weights are alpha I for client agent I. Again, I don't know who is good and who is bad. And ideally, I want that weight, alpha I, to be equal to 1 over the number of good guys. Right? There are 10 people. I want this weight to be 1 over 10 because that will be as close to the right thing as I can get. Does that make sense? Okay. In principle, you really want this weight to be non-zero for all of us because if I assign him a weight of 0, that's like saying you're choosing a restaurant for dinner today, ignoring his input completely. So you really don't want to give 0 weight to anybody. And ideally, you want to give equal weight to everyone. Right? That's the goal. Turns out that you can't achieve either of those. So you can prove that in the worst case, so you cannot, if you want to make a guarantee of non-zero weights, there's a lower bound. It says that if you want to tolerate 2 bad agents, up to 2 bad agents, you must be prepared to give weight of 0 to 2 good guys. So every bad guy basically eliminates a good guy because essentially you don't know who the outliers are. You don't know if they're on the left or you're on the right. So intuitively it sort of makes sense. And then this is an achievability claim. It says that if there are n nodes, n agents total, let's say n is 10, and I want to tolerate 2 bad guys, so t equal to 2. So 2 of them, I can, 8 good guys total. 2 of them, I may have to make them 0. So I can guarantee n minus 2t guys non-zero weight. That's sort of the best you can do. And what you really want to give them is roughly 1 over n minus t weight. N is the total number, t is the bad guys. If you were uniform, it would be 1 over n minus t. I can't do that, but I can come within a factor of 2. So it's a 2 competitive algorithm in that sense. So this is reasonably good. This is what we can achieve with distributed algorithms. And I'm not going to present the distributed algorithm today. I'll present a centralized algorithm where imagine that you have access to all the functions. So the agents, you are a server. Each agent tells you his own cost function, complete specification. And of course, one of the functions, if t equal to 1, is bad. If t equal to 2 of them are bad, you just don't know which 2. And your job is to take these cost functions, throw away the bad ones, and compute the optimum of the, over the remaining agents. Is the goal clear? And then you might want to do this distributedly. So this is, if these are the cost functions somebody gave you, you don't really know which 2 cost functions are bad. I'm allowing for t equal to 2, meaning two bad agents. These could be these 2, those 2, 2 in the middle. I just don't know which 2. And somehow you have to do filtering. And filtering is not a new notion, right? Filtering we do for many things. The question is, what should filtering mean in this context? That's sort of hopefully a new contribution. So the way I'm going to explain what we do is through this notion of a virtual cost function, gx, I'm going to define a new cost function as follows. So I have given you n cost functions, right? There are n agents. I gave you n cost functions. At every x, now this is computationally not really feasible, but just play with me. At every x, I'm going to compute the gradient of all the n cost functions, right? And then I'm going to filtering on the gradients. I'm going to throw out the outliers, smallest t gradients. I'm assuming, by the way, my arguments are scalar here. So I throw out the smallest t gradients, the largest t gradients, and then I average the rest. And that's the gradient of my virtual cost function. Okay? If your original cost functions, f1, f2, f3, are constrained to be convex, then turns out this virtual function is convex too. So you can apply your favorite algorithm to these gradients and find the optimum. And that algorithm, if you use, then you get this property that I just showed you. You can get this property. You essentially get the optimum performance from this algorithm. It's centralized, but you can implement similar algorithm in a peer-to-peer setting as well, where agents exchange gradients with each other. So I get gradients just from my neighbors, and then I apply the filtering rule I just showed you on the gradients that I receive from my neighbors in a peer-to-peer setting. This also works so long as your graph has sufficiently rich connectivity, and there is a certain characterization of the network graph that says under what conditions the algorithm is correct. It's a necessary and sufficient condition on the graph under which the algorithm will be correct. This is all shown so far in our work, when the arguments are scalars, the way I pose the problem doesn't extend to vector arguments, and we don't have time to get into why, the technicality, but if you want, I can talk to you offline. But the way I pose the problem to say that what I want to really compute is a weighted average of my initial cost functions. We are not able to solve that problem posed that way for vector arguments, but you can solve for vector arguments if you allow me something more, such as some kind of correlation between the cost function. For example, if I say all the cost functions are equal, you can see how that could be solvable, right, by just doing majority vote. So clearly, some correlation between cost function is helpful, and my student Lily has results, even recent results, in the context of machine learning now, where she's able to use a correlation between the different cost functions to solve this problem, even with vector arguments. But there, I won't go into the details of that because I know I'm out of time. So this is what we discussed today. So we have a notion of distributed optimization, either client-server or peer-to-peer. And the solutions that we have essentially apply to both settings. We have a new notion of privacy and a notion of fault tolerance that is, I don't think, fundamentally new, but at least the results we are finding are stated that look different from some of the other work on machine learning. So with that, let me stop. We have a bunch of papers and reports and archive, but you can get them from this website too. So with that, thank you, and please go to Shripa's poster this evening. Thank you.
Okay, so we already asked a few questions, but we have time for a couple of more. Any other questions? So in the last fault orders problem that you described, the special cases that you mentioned for vector cases, they also are easily doable in distributed settings, or?
So if your goal is to do just consensus with vector arguments and faulty inputs, faulty agents, for example. So let's step back. Let's not even say optimization. Let's just say just consensus. Okay, well, what do I mean by consensus? Each agent has an input, which is a vector, and you want to spit out an output that's in the convex hull of the inputs of the good guys. Except we don't know who the good guys are. Okay, that's the goal. If the graph is completely connected, meaning it's a click, so everybody can talk to everybody else, we know how to solve this problem. If the graph is incomplete, even that problem, we know how to solve it in some cases, meaning we have a condition on the underlying communication graph under which we can achieve fault-tolerant consensus, but we don't know that that condition is necessary. So necessary and sufficient doesn't match. That's the problem even for consensus alone. Now, if you come to optimization, there is a slightly different issue that I glossed over quite a bit, but maybe do I have another minute at least? Okay, so let me touch upon the technical difficulty. So take this cost function, and let me call this cost function as a feasible cost function. And by feasibility, what I mean is the following, that I am doing a weighted average over the cost functions of the good guys, where no more than t weights are zero, no more than t weights are zero, and the non-zero weights are lower bounded by that. Okay, so feasible functions are the good weighted average over the cost functions. Now, each of these feasible cost functions has an argmin, meaning it has a convex set in which that cost function is minimized, right? You take for each of such feasible cost functions, you have the optima. Take the union of all of those. Are you with me? So I have many such feasible cost functions. For each feasible cost function, I have optima. Take the union over all of them. If your argument x is a scalar, that union happens to be convex. If x is not a scalar, it's not convex. And that's where we run into some kind of trouble. Okay, so we can get quite far with vectors, but there is a point at which we don't know what exactly it is that we are achieving, actually. In the sense, we don't have a nice way of saying what we are achieving. So in a sense, the problem is open for vectors. Yeah.
Let's thank Nitin one more time.
Thank you again.